a pleasant day. So in this video, we will be talking about roots of equation in numerical method. So roots of equation, as what we know, is uh, finding x in algebra. No, we have certain equations in some sort of mathematical model. We have algebraic, we have polynomial, we have quadratic equations, we have trigonometric equations, we have logarithmic equation, exponential equations. So if we equate that to 0, then we try to solve the value of x. So that is what we call the roots of equation. And in visualization, as what we know, the curve or the line to whatever your equation is, it is the line or the curve that intersects to the x-axis at one point. So at what particular point that is our root. So you could say that there are also equations or line that intersects the x-axis twice. So we have many roots. We have at least two roots. We have three roots. It depends on what equations are we dealing with. So yeah. So now how do we execute or finding the roots of the equation in numerical method? So we have at least two main methods, which is the bracketing method and the open method. And yeah, we will be talking about bracketing method first. So in bracketing method, you have at least three uh, forms of bracketing method. So one, that is graphical, two, that is bisection method, and three, that is false position method. So let's go first with the graphical method. So I think I will not read this. These contents are coming from the book of Chapra. But however, how I describe the graphical method is that uh, when you have a certain equation and you try to plot, say you have the domain and the range, you have sets of x, set values of your x or set of values of your domain, and you substitute your values of your domain to the function, then you have again pairs of x and y, and you plot it out in a Cartesian plane, and then you have a line there, and by observation or by investigation, you look to where the curve or the line intersects with the x-axis, then that is our curve. I know that is our root. So yeah, so that is how you find the root in graphical method. So we have here example 5.1. So this gives you already the equation of the drag coefficient to where the given values are already put in the equation 5.1. Let's say that yeah, that is 9.8 times 68.1 all over c times 1 minus exponential of negative c all over 6.1 times 10 close parenthesis minus 40. So this equation came from the free falling body, no? And then there is a drag coefficient that giving you a delay on going down, no? In the case of a parachutist, no? So it prevents him to to go down fast because of the parachutes that supports him. So yeah, so this is the equation, no, coming from the theories that he got in physics. So he declares his governing equations, then he try in graphical method, he tried to have series of values of c, since we are using c as our variable for your drag coefficient, and function of c, no, as the values that we substituted with the c. So you have a series of values of c, which is the gap are 4, no, that is 4, 8, 12, 16, and 20. And you substitute that value to your equation, then you have pairs of values for your c and f of c. So if we plot this graph, if plot these points on table, you have this visualization of graph. So through investigating, you determine the root, that your root is between 12 and 16. And by looking also in the table itself, you know that it is between 12 and 16 because, yeah, the value of around 12 is around 6, yeah, and it goes below the line because it becomes negative. So your root is somewhere between 12 and 16, or maybe around 14, as you could observe in the graph. So that is how you find the root of equation out from graphical methods. It's quite conventional because you are trying to just you are trying to look at it or trying to investigate by looking at the graph. So of course there are great errors of it based on how your eyes could look into the graph, or based on how you plot the graph. So it depends, no? But you could say that your estimate is around 14, and if you don't really need a very accurate one, then that could be a good estimation of the value of the root of the equation. So next one, yeah, so these are graphical presentations, no? When the line, or when the curve or the line meets the x-axis many times, then you have multiple roots of your equations. You have a as many as it intersects, you have as many roots for that equation. Same scenario with your b and your for letter c, so you have at least two roots, no, for that equation. So yeah, so that is the graphical method. So let's proceed with bisection method. So bisection method, um, it's different from the graphical method, no, because we are just looking at the graph. Here in bisection method, we are trying to calculate to find the root. Okay, so in the figure that you can see, this is actually the depiction, no, of the bisection method. So I think in this graphical presentation, I think you still cannot understand the how or the algorithm of the bisection method. So I think I should give at least my description on how I understand it. So let's say this is the Cartesian plane, no? So pasensya akong drawing. So yeah, so this is your, let's say, your curve, no? Ana siya. And so by graphical method, you could say that your root is this one. This actually is your root. But in bisection method, you need actually two at least values, or what we call as brackets. So two values that could bracket your your curve here. So let's just say this is your bracket for the lower guess, and this is your bracket for your upper guess. So given the situation, and what we could see, that your bracket, inside the bracket is, you could see that there is your root here. So let's just say your bracket is safe, and with continuing the calculation, you could actually find your root. So yeah. So as we go on, in bisection method, we are trying to take the half of the bracket. Let's just say this is the half of the bracket. So what happens now is you have 3 points here, this one, and this one, and you need to update your brackets. So as we observe in this situation, you need to erase this one and update that this is your new lower bracket or new lower guess, because it is much near to the root. And if you choose to replace this one, you're taking half of it in this, you're taking consideration in this bracket where there is no root. So you should replacing b, the lower bracket than the upper bracket. Then continuing, so taking the half na pod. So let's just say that you will be replacing again this one and updating that your upper bracket this is this one, and so on. And as you can see, you could, yeah, erase again this one. You could see that you are going closer to the root. So at the kapila na ta nag-erase. So at the third, at the fourth time that we taking the bracket, we are very much closer to the root. And that is how the bisection method works. So there is actually a standard step on how to solve the root, no, of the equation. So first and foremost is that you have to choose your lower and your upper guess. So it's kind of safe, no, if you have graphical presentation, no. Okay, if you have graphical presentation, at least you have a certain or accurate guess, that you could say that if your bracket is within that, there is a root. So you have to choose, no, for lower and upper guesses for the root that the function changes sign over the interval. So this can be checked by ensuring that uh, substituting your lower and upper guesses to your function and taking the product of it. So it should be lesser than 0. So if it is not lesser than 0, then you should reconsider. Then step 2, since you have already your upper and lower guesses, now what we did was bisecting the bracket, no, and the graphical presentation. So in calculation is that we are trying to take the average of the two guesses that we consider, okay, and or taking the average of the guesses, no, or dividing it to 2 after adding or taking the sum. And once that we get your XR, no, katong average, so that is XR. So R, I think, stands for the word root, L stands for the lower, and U stands for the upper. So in step 3, you need to update your lower guess or your upper guess should be replaced. So how you will know that it should be replaced, the lower should be replaced or the upper should be replaced, by not looking at the visualization, just by calculating it. So there are at least 3 conditions, no. So first and foremost, if the product, no, after since you have the value of substituting to the upper and the lower guesses, you need to substitute also the new calculated x or the x sub r to that function. So you have f of x sub l, f of x sub u, and f of x sub r. So if you take the product of f of x sub l and f of x sub r, in this situation, kani akong kipasabot, If the product is lesser than 0, then the root lies in the lower subinterval, and so therefore you should replace your upper guess with the new calculated x, or the root. And if it is opposite, if it is greater than 0, then you should be replacing the lower guess instead of the upper guess. So it's the opposite thing. If it is equal to 0, then you accidentally find the exact value of the root and does not or should not continue in calculation. You should stop the calculation. So you declare that your calculated x is the root of the equation. So if does not equals to 0, usually it does not happen. So you will continue in calculating. So since you are replacing your x sub u or your x sub l, your upper and lower guesses, with the new calculated x, so you are taking again the average, no, of yeah, your x sub l and x sub u, knowing that one of it is already updated. You divided it to 2, and you have new calculated x sub r, and you again follow the descriptions of how to determine, or how to or what guess should be replaced, so on and so forth. So I think yeah, this method is well explained. So uh in some example, so same scenario with the first problem from the graphical method. So let's just say that you have 12 as your lower guess and 16 as your upper guess. So since it's kind of safe that you should declare in that particular guess, because from the graphical method, that is between to 12 and 16. So safe siya i-declare that it should be 12 and 16. So when you calculated your x sub r, you know that the equivalent value is 14. So this one, okay, and you yeah, you try to calculate, no, so after getting the 14 value, you try to substitute that value to this equation. So that is equivalent to 1.569, and your f of 12 is around 6.067. When you multiplied both, you get a product of 9.517. And where should that new root or new x, calculated x, should be replacing to? So in looking at the situation here, it is greater than 0. So that is to replace your lower guess, right? So you have now your lower guess. So let's say now your x sub r is uh 14 plus 16 all over 2. That is around 30 all over 2, or is equals to 15. And that 15 is substituted again to this equation. Then you multiply it with uh uh yeah, f of 14 kani siya, no? So f of 14 times f of 15. So if that is greater than 0, so you should replace f of 14. So if it is lesser than 0, then you should replace the f of 16. I know, yeah, the what I mean is that you should replace it with the lower guess. So if it is lesser, you should replace the upper guess. So, this is how he managed to calculate, no? So, kato, no? So, 15. So, moto, he find it that where the product becomes negative 0.666. So, it is lesser than 0. Then you should replace the upper guess, which is 16. So, now your new root should be, and your new bracket should be 14 and 15, right? So your new root should be 14 plus 15 divided by 2, which is 29 all over 2, or 4.5. So you have now the value of your new root, so you need to find f of 14.5 multiplied by f of 14, then decide again. So it's kinda repetitive situation, no? So may 14.5. So until he managed to get closer to the value, no, of the root. So I don't know what is the value of the root in analytical method, but I'm sure that it is very near to around 14. So the more calculations, as we can see, the more our root value will be accurate, no? So in the first matter is that we have an integer, so we have a whole number here. We have 14, then we come 15, and now we go with one decimal value, which is 0.5, so 14.5. So we try to go on, we have more accurate data, no?